Today we would like to see the Digital Electronics and Microprocessor System Elec211 Lecture 9, Lecture 11. So today we would like to see what is subroutine, what is a link register, what is a branch, what is the link branch BL, the branch and exchange BX, the branch and link and exchange, the nested subroutine. So the stack, the net push pop instructions, and so forth. So the subroutines, many microprocessor programs include the groups of instructions which may be repeated many times, and it's a wisdom of the memory to include this instruction in the program again and again. Instead, it can be included once in a special structure known as the subroutine. So the main program branch to the start of subroutine is the main program branch to the start of the subroutine. The main program branch to the start of the subroutine when required. At the end of the subroutine, there is another branch back to the main program. That's very simple and intuitive. For example, let's see if you are doing here, and you're branching here, and you're coming back here. This is the branch, and this is called subroutine. This is the main program. So a program requirement is to be able to branch to a subroutine where it is possible to resume to the original code. For example, like say that we are going a program instead of doing instruction 1, instruction A, instruction B, instruction C, instruction 2, instruction 3, instruction A, B, and C. While doing that, we define the main problem. Instruction 1, branch 2, the subroutine A, B, C, and come back to the instruction 2, come back to the instruction 3, and subroutine A, B, C, and come back to the main problem. So let's talk about the link register. At the end of each subroutine, how does the processor know which instructions are returned to? The program is use the link register that holds the memory address of the instruction in the main program, which the subroutine returns to. The value of the program counter will be saved in the register. The ARM Cortex-M0 microprocessor, the link is the link R14. So that is very important that the microprocessor ARM Cortex-M0 uses the register R14. It can be replaced by LR in the mnemonics. So the link register is just like how does the program know which instruction to return to, and this is solved by using the link register. It's just like after doing the subroutine, you need to know which instruction to return to. This is like you know your who you are going to be, which just like what if you are maybe study abroad, and you just need to know that where should I come back. So the branch and the link is the mnemonics for the branch and link is called BL, and that's like a BL to a larger address, and the target address can be a label. And the BL instruction use 32 bits immediate. It is the 32 bits. So the BL instruction uses 22 bits immediate, and it is 32 bits and 4 bytes machine code. So I'm not sure why it's 32 bits. BL uses 32 bits. That's very interesting. Let's look at this. BL, right? 211. I must finish this as soon as possible. Why BL instruction is 32 bits immediate? and it uses and it's 32 bits or 4 bytes machine code.我是打的32 bits immediate mean. And bytes. So the range of the destination of the BL instruction is plus or minus 16 megabytes relative to the current value of the program counter. So that is the memory address of the BL instruction. So branch and exchange. To return to the subroutine, the value of the link register is moved to the program counter using a branch and exchange instruction. So BXLR and BXR14. So LR and R14 is basically the same. And the branch exchanges instruction is move the value in the register as Z into the program counter R15. The register RZ can be any of the 16 registers, and there is no resistance on the destination of the BX branch, and the links register is not updated. There is no registration on the destination of the BX linked to the any. The link register is not updated. Why link register is not updated? Why? So let's continue look at the branch link exchange. The branch with link and exchange execution is BLXRZ. It's move the value from register RZ to the program counter R15. And it updates the link register R14 with the return address. And the machine code for the BLX instruction is 16 bits or 2 bytes long. There's no registration on the destination of the BLX branch. So the subroutine is just like, what if we have subroutine here, the main program here, and we go to the subroutine, we do some execution with the BXLR coding instruction 4, and yes, so this is the LR, we come to here, and the go to instruction, and we go here, and we go back here. During the first part of the subroutine with the link, register holds the return value of the 8006, and during the second part, the return is 200E. So in this case, let's look at this basically the same thing that we're going to start the subroutine here, and we're going back to here. So the first form is after the first execution, the addds instruction is OX0000FC8. And now we are going to look at this. What is the ADDS? When the ADDS is, so this is a good answer. And the answer is just like when doing the ADDS, we actually the link register after the subroutine X called twice, and the add is the first part, but before the second part, the link register R14 is returned by the first part is OX0000FC8. So that is the thing. I think it's very easy to see that just the next instruction after the branching factor. So let's look at that. What is the value stored in the link register 14 when the sub register is executed? Let's say SUBS. Let's say the SUBS is here. The next one is FD0. So the correction answer is FD0, and with the same logic. And the next is subroutine is just like we can have occur if a branch and a link occurs during the execution of the subroutine. The value of the link register may be overwritten by the new return. Before one subroutine calls another, the link must be stored somewhere. And the link register can only hold one return address at a time. And if a subroutine is called the subroutine B register cannot store the return address for the both. Just like if you are going the nested calls, you must do that. You do that. You cannot, update elsewhere. The nested subroutine is a complicated program. May have several subroutines. Some subroutine may call other subroutine. Is a standard practice and known as nesting. In order to preserve the return code from subroutine, the area of the computer memory is called the memory stack. Oh, the memory stack is used. Oh, I see. So, do you know the reason why we need this program stack? Is that we want to store the address. To store the address of the nested code. So the stack is first in, last out. Oh, that is very similar to the nested code, right? There's the first in, last out. So that is used for storing the nested address, the address of the nested code. And so in terms of the stack, we have several concepts to be clarified here. So the stack is first in, last out, right? If you value in, value in, value in, value out, okay. And we can push, and the stack has two operations to be executed, which is push and pop. We can push it, pop it. And the stack pointer holds the address of the memory that is on the top of the stack. This is a very important concept, that the stack pointer holds the address of the memory that identifies the top of the stack. The address is either the location of the last data to be pushed onto the stack, or alternatively the location of the next empty. Two alternatives are known as the full stack and the empty stack. So for example, if it is the empty stack, it is the next one to be the next empty one. So what if it is the next empty slot? And what if it's the full one, it's just the last data. The last data means 最后一个 data. Okay. But that is the last data. That is last data. So we can do the ascending and the descending stack. The stack can be either ascending or descending. For descending stack, the memory address of the top of the stack is less than the memory address of the bottom stack. So the data is pushed onto the ascending stack, and the value held by the stack pointer decrease. When the data popped from the descending stack, it increase. The descending everything is like normally if we push it in, it should increase. But what if we push it in, it decrease. Ascending stacks works in opposite way, and the top is higher memory than the bottom. So the basic thing is that the memory address, this one is larger, this one is short, and this is smaller, this is larger. We are using the descending stack, but the top and I see. So the thing is that the memory address is the same. This address is the same as this one, but we define the top here and the bottom here. Okay, I see. And the stacks and the ARM Cortex M0. The ARM Cortex M0 uses the ascending stack. The register R13 is used as the stack pointer. to push the linked address onto a full ascending stack. The mnemonics push LR the pop the value from a full descending stack back into the link register. The mnemonics is pop LR. Because why we cannot do that? Because the LR it stores where you should go after your trip, right? If you pop it out, you do not know where to go. You are lonely, my friend. So let's do the stacks and the ARM Cortex M0. The first instruction, the subroutine, is generally push LR. There's any branch factor that links the subroutine can be overwritten by the link register. The subroutine ends by popping the return address from the stack onto the program counter. Pop PC is equivalent to pop LR followed by moving the value into the link register onto the program counter. Therefore, pop LR is not required. The stacks and Cortex M0 is common it is common practice to pop the return address directly onto the program counter using pop PC. Pushing and popping the stack can be achieved with several registers at the same time. The lower register R0 to R7 can be used in addition to the link register LR or R14 with push. The lower register R0 to R7 can be used in addition to the program counter PC or with pop. So the thing is very simple that as long as you can push it, so R1, R5 to R7 and LR, and we pop it just R1, R5 to R7 PC, just to make sure that these two are the same, and push is linked with LR, pop is linked with PC, and we can stack every other register that well, but the only thing you see that the numbers of values, the numbers of registers must be the same, and the stack or other registers, we can push them here and just push them in, and we just push them in, and R0, R2, LR, and we can stack for other registers. So that's all for this.